let's start. Today we have a talk by Hongliang Jiang, and he will speak about infinite symmetries and warped identities in celestial holography. So please start.
Okay. So first of all, I need to thank the organizer for inviting me to speak here. Today, I'm going to talk something about celestial holography. So the title is Infinite Symmetries and Warped Identities in Celestial Holography. So this talk is based on these three papers, and especially the first two. So we all know that ADS-CFT correspondence is wonderful. So this is conjectured to be an exact duality between quantum gravity in ADS and the gauge theory. And it has been tested precisely in the past 2 decades, and remarkable agreements were found. So by studying this ADS-CFT correspondence, we have learned a lot about the quantum gravity. For example, the connections between entanglement in field theory and the space-time geometry, as well as the famous black hole information paradox. On the other hand, this ADS-CFT correspondence is just one special example of the more general holographic principle, which was originally motivated from this black hole entropy. And according to this holographic principle, the quantum gravity is holographic in general. So it's natural to wonder, do we have a holographic picture for other quantum gravity? In particular, do we have a holographic picture for quantum gravity in the absence of cosmological constant, namely flat holography? So this is a very natural generalization, but it's very difficult. And this is partially due to this null and non-smooth boundary here. But in recent years, a new program called the celestial holography study to emerge. And this offers a new and interesting avenue towards a flat holography. So what is celestial holography? So in ADS-CFT, we can compute this, compare the correlation functions on 2 sides. So in ADS, the natural observers are the boundary correlators. Here, I'm studying this Minkowski spacetime. So the natural observers are the scattering amplitudes. In particular, in this talk, I will focus on the massless field scattering in 4-dimensional spacetime. So in the traditional framework of studying this scattering amplitude, so we need to keep track of the evolution of these particles from the past to the future. However, this S matrix itself is defined as a map from this past non-infinity to the future non-infinity. So it's naturally to wonder, do we have a holographic way of computing this S matrix without going to the bulk? And indeed, this is possible. So we can represent each particle here in terms of an operator on the so-called celestial sphere, which lives at a non-infinity. So here we have 5 particles, so we have 5 operators. And to evaluate the scattering amplitudes on the left-hand side, we just need to consider the correlation functions of this set of operators in the so-called celestial conformal field theory. So the essential point of celestial holography just says that the 4-dimensional S matrix equals to 2-dimensional CFT correlator. Obviously, this can be generalized higher dimension, but in this talk, I will focus on 4-dimensional spacetime. So the celestial holography just offers a new paradigm for flat holography beyond the traditional framework of ADS-CFT. For example, here we have this 2-dimensional difference between the bulk and boundary, which is different from this ADS-CFT. And also, this is a new formulation of scattering amplitudes. And by studying this celestial holography, hopefully we can gain some new insights about the quantum gravity. So the main motivation of this talk comes from the following question. What are the 4 underlying symmetries governing the scattering amplitudes in flat spacetime? So we all know that this symmetry is one of the most important guiding principles in physics. Actually, the whole story of this celestial holography is about symmetry. It was motivated from symmetry. So people first observed that these soft theorems can be regarded as warped identities associated to these BMS symmetries. And later people even realized that we can reformulate the whole program of scattering amplitude by introducing the so-called celestial amplitude. And this celestial amplitude has manifest Lorentz symmetry. and it's different from this momentum space amplitude, where the translational symmetry is manifest. Nevertheless, we still don't quite understand the symmetries. So the question is, what are the 4 underlying symmetries governing the amplitudes in flat holography? So this is the outline for the rest of the talk. So first, I will introduce some basic knowledge about the celestial holography and the celestial amplitude. Then I will talk about the symmetries. So I will discuss the global symmetries and asymptotic symmetries. So for the asymptotic symmetries, instead of traditional way of analyzing this asymptotic symmetry from the bulk, I will use celestial holography. So more precisely, I will derive infinite dimensional symmetry algebra from celestial conformal field theory. And this algebra is called the holographic Chiral algebra, arising from this soft sector of the operator product expansion. I will also derive the infinite word identities associated to this infinite dimensional symmetry algebra. And finally, I will conclude. So let me start with kinematics. So as I said, I'm interested in the 4-dimensional scattering amplitudes. So especially the massless field scattering. So the massless fields have null momentum, which can be parameterized as follows. So we have this null momentum P mu. It can be written as the product of both 3 pieces, epsilon, omega, and Q. So here, this epsilon equals to +1 or -1, depending on whether the particle is outgoing or incoming in the scattering process. And omega is essentially the energy around this null direction, Q mu. And Q mu is a null vector. It's a function of this Z and Z bar. Here, Z and Z bar are the coordinates on the celestial sphere. So because I'm considering 4-dimensional Minkowski spacetime, the celestial sphere is 2-dimensional. So Z and Z bar are just coordinates on this S2. So this Q mu just builds up a connection between the null direction in 4D Minkowski spacetime and the points on the celestial sphere. So if we perform a SL2C transformation, namely if we just transform Z to AC plus B divided by CZ plus D, and similarly for Z bar, then you will find that this momentum P mu will transform in this way, and also this omega. So this is just the Lorentz transformation for the momentum. So this is not surprising because we have this Lorentz group in 4-dimensional spacetime, which is SO3,1. And this SO3,1 is just this SL2C, which is just a conformal group of on the celestial sphere. And also this null vector Q mu is useful for other purpose. We can use it to construct polarizations. For example, for gluons, we can take Q mu and we can pick up Q mu and take derivative of Q mu with respect to Z, and then we get a gluon polarization with positive helicity. If we instead consider the derivative with respect to Z bar, then we get a polarization vector for negative helicity gluons. And if we first consider the product of 2 gluon polarization, we get the polarization tensor of graviton. So now we can introduce a celestial amplitude. So in this translational momentum space scattering amplitude, we have manifest translational asymmetry, as can be seen from this delta function. So this delta function enforces the momentum conservation, which is just the manifestation of translational symmetry. Now we can take this momentum space amplitude and perform Maillard transformation, and this gives a celestial amplitude. So here we have this momentum space amplitude. It has n external legs. So for each external leg, we perform a Maillard transformation, and this gives Mn, which is the celestial amplitude. So this looks like a very simple rewriting, but it has some interesting physical implications. In particular, this celestial amplitude can be regarded as the correlation function of this set of operators in the so-called celestial conformal field theory. So here, each operator represents a particle, And this operator is labeled by several pieces. This is delta is a dimension, and J is a spin, and epsilon equals to +1 or -1. So by performing this Maillard transformation, we just go from this momentum eigenstate to this boost eigenstate. So if we consider supersymmetric theory, then we can introduce fermionic coordinates in the scattering amplitude. And doing this Maillard transformation will give rise to the celestial super amplitudes. This is very useful for supersymmetric theory, like N equals 4 for Yang-Mills, as I will discuss later. We can also consider different limits of this scattering amplitude. For example, we can consider the soft limit. Then in this limit, we have this soft theorems. And doing this Maillard transformation will give rise to this word identity in celestial conformal field theory. Similarly, we can consider the collision limit, where two particles are becoming parallel. In this limit, this scattering amplitude will become has this factorization property, and performing a Maillard transformation enable us to extract the celestial operator product expansion. So both word identities and OPEs are very standard concepts in CFT, and I will discuss more details later.
I have a question. So what is the meaning of these deltas? So
delta is conformal dimension.
Yeah, but how they are related to original amplitude is just, you have massless particles, you parameterize momentum by omega and q, right? So yes. What's the intrinsic meaning of delta? What's its interpretation from the amplitude side, from the original scattering amplitude? Is it kind of just artificial trick, or do you really need this Maillard transform, or that's a way to realize conformal group more explicitly?
Yeah, if you do this Maillard transformation, then this celestial amplitude can be regarded as this correlation function, which makes this Laurent symmetry manifest.
Yeah, but my question is, why deltas, for example, are discrete? It looks like a completely artificial concept. You're just making this Maillard transform in omega and then introducing these deltas. So if I just start with the original amplitude with 4 momenta, how do I know which deltas I need to consider? Or maybe I'm misinterpreting what's the meaning of this relation.
This delta in this celestial conformal field theory, if you want to expand the particles in this boost eigenstate, so to form a basis, this delta should be 1 + I lambda. So it's not a discrete.
Okay.
But we will normally consider the analytic continuation. So delta can be generic complex numbers.
Okay. All right. Okay.
Yeah, I will discuss later. So.
Okay.
Sorry, and why do you say that Laurent symmetry is manifest?
Yeah, because this becomes this conformal symmetry, and if you write this correlator, then by construction you have this conformal symmetry, right?
So what happens to delta under Lorentz transformations? So omegas are not invariant, right? So it's just energy, so it's not invariant.
Then if you perform this Lorentz transformation, omega will transform in this way, but delta is invariant under this SL2Z or Lorentz transformation.
Okay, thank you.
Yeah, so let me first discuss global symmetry, which includes Poincare, conformal, and superconformal symmetry. So first, I discussed this Poincare symmetry of momentum space amplitude. So we consider the scattering amplitude of relativistic quantum field theories, which have this Poincare symmetry. So this scattering amplitude should also be invariant under this Poincare transformation, including translation and Lorentz transformation. So this invariant properties can be written in terms of these 2 equations. The first one implies this translational invariance. So we have this translational generator P mu, it acts on this scattering amplitude in moment space. So here, this subscript j means that this generator only acts on this j external leg. But finally, we also need to take the summation over all j. So we need to consider the action on all the external legs. And this should be 0 if the amplitude is translational invariant. So in moment space, the generator P is very simple. It's just the momentum P mu. So if we insert this P mu here, then this scattering amplitude will trivially satisfy this equation because of this delta function. But for Lorentz transformation, we have this Lorentz generator M mu nu. So in moment space, it's given by this P mu times this derivative with respect to P nu, and we need to take the anti-symmetrization of mu and nu index. So this Lorentz generator will also act on this amplitude, and the invariance means that this is 0. So a priori, it's not obvious whether this is indeed 0 or not. So this means that for this structure, we have this manifest translational symmetry, but the Lorentz symmetry is obscure. And now we perform this Marian transformation and obtain this celestial amplitude. So since we just do a simple integral transformation, so this celestial amplitude should also be invariant under Poincare symmetry. But now we need to find the generators of this Poincare, the form of these generators in this celestial basis. So for example, now this translational generator is given here. So it's given by the product of Q mu times e to the d delta. So this e to the d delta just implements the shift of dimension by 1. So if it acts on f delta, then we get f delta plus 1. And this can be seen as follows. So for the translational generator in moment space, this means the insertion of momentum p here, and p can be written as product of omega and q. So this means this delta j will shift by 1. So this explains this e to the d delta factor, and this q mu only depends on z and z bar, so it's left untouched in this integral transformation. So we also have this q mu here. So but if we just use this generator and act on this celestial amplitude, it's not obvious that this is 0. So this means now the translational symmetry is obscure. Let's switch to this Lorentz transformation. So in this basis, this Lorentz generator is given by L, K and L bar K. So K is -1, 0, and 1. So there are 6 generators, which is either the number of generators for Lorentz group. So explicitly, this Lorentz generator in this celestial basis is given here. So you can compute the commutators, and you will find that indeed this satisfies algebra SL2C, which is isomorphic to SO3, namely the Lorentz group in 4-dimensional Minkowski spacetime. So here, this equation is just means infinitesimal invariance of celestial amplitude under the infinitesimal transformation. If we promote this infinitesimal transformation to finite transformation, then we will find these equations. So we perform SL2C transformation on this C coordinates. Then this is related to the celestial amplitude without transformation, but it's multiply with this factor. So if you are familiar with 2D CFTs, then you know that this is just the transformation behavior of correlators in 2D CFT. So this means that because of Lorentz symmetry, this celestial amplitude can be regarded as a CFT correlator. So we have this formula I showed you before. So this celestial amplitude can be regarded as a correlation function of this O delta J's in the so-called celestial conformal field theory. So here, delta and J are the conformal dimension and the spin of this operator. So in particular, because now the celestial conformal field theory is 2-dimensional, so we have this holomorphic path and anti-holomorphic path, and they have different weights, H and H bar. So this delta G and H bar are related in a standard way. So in particular, this spin J equals to h minus h bar. This is a spin in 2D, but it also coincides with the helicity of particles in 4 dimensions. So we have this conformal dimension delta. So which in order to form a basis for the Y function in the scattering process, the conformal dimension should reside in the principal series of SL2C. So namely, this delta equals to 1 plus I lambda, and lambda is real. But it's useful to perform analytical continuation of delta on the complex band. Then this delta can be generic complex number. So far, we discussed Poincare symmetry. Now we will consider conformal symmetry, because we know some series also have has some conformal invariance, like this 5-4 series in 4D, at least classically. So here I'm talking about the bulk conformal symmetry, which is different from the conformal symmetry on the celestial sphere, which is induced from the bulk Lorentz transformation. So in this case, it's useful to use a spinor helicity formalism, because for massless particle, we have this null momentum. Then we can convert this null momentum into a 2x2 matrix. And because this momentum is null, it can be written as the product of 2 spinors, lambda and lambda tilde. Both 2 spinors have 2 components. So we can similarly introduce the following set of spinors, P, P tilde, K, and K tilde. So they have 2 components. For example, P alpha has 2 components, 1 and Z, and multiplied by this E to the DH over 2. So here E to the DH over 2 also implements a shift of dimension by 1/2. So we can take this P and P tilde, then from this consider their product. Then we have this P alpha and P alpha dot. So this is related to this P mu through this Pauli matrix. If you work out the components, you will find that indeed we recover the previous translational generator in celestial basis. So this is for translation. And now we have this K and the K tilde here. And for K, we have 2 components, dz and zdz plus 2h minus 1 multiplied by this shift operation. As translation, we can consider the product of K and K tilde and form this 2x2 matrix. And then we can convert to this K mu. And this is just a special conformal generator. And we can also consider this product of P and K. So we take a K alpha, P beta, and then we take the symmetric transition over this alpha and beta. So we get a symmetrical matrix alpha beta. This, if you work out the components again, then we'll find this coincides with the previous Lorentz generator. Similarly for this L alpha dot beta dot. And finally, we have this dilatation. In this case, is given by this 1 delta. So it's very simple. So with this conformal generator, we can then compute the commutators, and then you will find that indeed they satisfy this conformal algebra SO4,2. So this gives the conformal generator in celestial spaces, and it can act on celestial amplitudes. And furthermore, I'm now going to consider supersymmetric series. In particular, I will consider N=4 super-Yang-Mills theory. This theory enjoys maximally superconformal symmetry PSU 2,2/4. And this huge amount of symmetry imposes a huge amount of constraints on the structure of amplitudes. And in the past 2 decades, people have made a tremendous progress on the scattering amplitude of N=4 super-Yang-Mills. So we have compute the amplitudes up to a very high loop order. And we also find a lot of underlying mathematical structure. So for this N=4 super-Yang-Mills, there are a lot of degrees of freedom. So in particular, for the consideration of scattering amplitude, we need to study the on-share degrees of freedom. And all these on-share degrees of freedom can be packaged into an on-share swirl field by introducing this Grassmann variables eta a. A goes from 1 to 4. So we have this set of on-share degrees of freedom. So for example, here we have G plus, which is gluons with positive helicity +1. And also here we have G minus, which is also gluon, but now the helicity is -1. And both of them transform in the singlet of R symmetry. And in the middle, we have this anti-symmetric scalar. So in total, we have 6 scalars. So they transform in the anti-symmetric representation of SU4R. And for scalar, the helicity is 0. And finally, we have fermions gamma and gamma bar. So they have helicity +1/2 and -1/2. So they transform in the fundamental and anti-fundamental representation. And with this Grassmann variable eta, all these component fields that can be packaged together and form this on-share spur field. So we can take n on-share spur fields together and form this combination. And this gives a super amplitude. So if we perform this expansion over these Grassmann variables, then we can compare the coefficients and we then find all the component amplitudes. So this means this on-share spur field offers a very compact and powerful way of writing down the amplitudes in N=4 for Yang-Mills. So now I'm going to study this superconformal symmetry in the amplitudes of N=4 for Yang-Mills. So I will first discuss this momentum space. So in momentum space, all the superconformal generators are given here. So we have this lambda tuba, which are the spinors in the spinor helicity formalism. So we can take the product of this lambda tuba, then this gives a translational generator. And here we take derivative with respect to this spinor, then we get this special conformal transformation. And here, this is the dilatation. This is the Ron's transformation. And this is a conformal subgroup. We also have supersymmetries, supersymmetry generators. So this can be obtained by considering the product of spinors and the Grassmann variables or derivative with respect to Grassmann variables. So we can consider various combinations. Then we find this Q supersymmetry generator and S supersymmetry generator. And we also have this R symmetry generator, which implements the rotation in the R symmetry space. They can be written in terms of this eta and the derivative with these Grassmann variables. And finally, we have this combination. It looks complicated, but if we act this generator on the on-share spur field on super amplitude, then this is essentially 1. So with the explicit structure of this generators, we can compute their commutators, and one can show that they satisfy this PSU 2,2/4 algebra. For example, we can compute the anti-commutator between Q and S. Then we will find this asymmetry generator, Ron's generator, as well as this one. So because if we consider the action on the on-share superfield or superamplitude, then this omega is 1. So we only have D here, and this just gives a standard PSU to 2,2/4 algebra. So with this explicit expression for the superconformal generators, then we can act on this on-share the super amplitude. So we have many different generators, so we have many different expressions, but all of them should be 0. So this gives the superconformal word identities, and it imposes a greater amount of constraint on the structure of super amplitudes. So this is in momentum space. Now I'm going to find the counterpart in the celestial sphere. So we can start with this on-share spur field and perform Milling transformation, and then this gives this celestial spur field. So in components, it can be written in this way. So we have this same kind of field content, but it's transformed to the celestial basis. And furthermore, you see that here, the holomorphic weights and anti-holomorphic weights are different for different components. If we consider their sums, then you will find all of them have the same conformal dimension. So which means that all components share the same conformal dimension. This is what we want. And if we consider the difference between holomorphic and anti-holomorphic weights, then you will find they are different. For example, here the spin is h minus h bar, and this should be 1. And for this one, we will find this spin is 1 minus 1/2, so it's 1/2. This is indeed the helicity of this formulas here. And for scalars, similarly, we'll find that the helicity is 0. And this has a helicity of spin minus 1/2, and this is minus 1. So we found that with this kind of structure of h bar, we indeed have the correct helicity for each component. So this is a consistence of this celestial supersphere. So we can take n celestial superspheres and put them together, and this gives celestial amplitude, celestial super amplitude, which can be obtained from the Main transmission of super amplitude in momentum space. So we want to find the superconformal symmetry action on the celestial super amplitude in celestial basis. So as before, we first introduced these spinors, so k hat and the k2 hat. Yeah.
So I didn't really understand. Are you saying that n equal 4 Yang-Mills has a different PSU2,2/4 symmetry, or is this a rewriting of the usual superconformal group in celestial coordinates?
Yeah, it's essentially the same PSU2,2/4, but now I write this generator in a different basis.
Okay, so what is the question?
So the question, you mean why do I study this celestial amplitude, super amplitude in X4?
Yeah, as in, like, are you trying to show that the correlated?
Yeah, because I want to understand the symmetries on the celestial sphere, and we know that in momentum space we have a lot different kinds of symmetries, and these symmetries impose very strong constraints on the structure of momentum space amplitude. But now I'm interested in celestial amplitude, so I also want to find a similar constraint on celestial amplitudes. But as the first step, I need to work out the generators of those symmetries on the celestial sphere.
Okay, thank you.
Yeah, so now we need to now we talk about the superconformal symmetry in celestial basis. So we have this k hat and the k tilde hat, which are very similar to the previous k and k tilde, except for the extra eta ada parts. This is we have this piece because of supersymmetry. In particular, more precisely, this is to take into account the fact that the different components have different spin. So with this k hat and k tilde hat, as well as the previous p and the p tilde hat, we can form all the superconformal generators in the following way. So this translational generator is the same, and this special conformal generators are also very similar, except that we now need to take into account this eta ada, and we have this similar construction for this D and Rollins generator. And this asymmetric generator is the same as asymmetric generator in momentum space, because this main transformation just changes something in momentum space, but leaves the eta space, the asymmetric space invariant. And we also take different combinations between this P and K hat with these Grassmann variables, so we can form supersymmetry generators. So these are the very explicit structure of this superconformal generators. And then it can act on this celestial super amplitude, and this should be 0. And this is just superconformal order identities in celestial basis. So in particular, we can consider this Lorentz transformation. So previously we have a similar kind of equation. So we just perform SL2C, then we will find the actual basis here. And now because of this eta ADA, we also need to transform this Grassmann variables eta. So this means this celestial superamplitude can be regarded as some kind of superconformal correlator. So we just put n celestial superoperators here, and then we just evaluate them in the celestial conformal field theory. So here I add this quotation marks because the supersymmetry on the celestial sphere is different from the standard supersymmetry in 2D. So in the standard case, the supersymmetry is essentially the square root of translation in 2D, but in the celestial sphere, this 2D translation is somehow related to the 4D rotation. But for superconformal symmetry, the supersymmetry is induced from the bulk, which is the square root of translation. So this is the difference between this celestial superconformal symmetry and the standard superconformal symmetry, and why I just use the quotations here. But nevertheless, it's kind of a correlator. So this finishes the global symmetry. Now I'm going to talk about asymptotic symmetry. So in the study of celestial holography, so the central object is this operator O delta J. So this delta belongs to 1 plus I lambda IR, as I said before, to form a basis. But then now I analytically continue on the complex plane. As a result, these celestial operators can be classified into 2 categories: the soft operator and hard operators. So for the soft operators, the conformal dimension K coincide with J or J-1, J-2, etc. And furthermore, we can consider soft current, which is constructed as follows. We take this O delta and multiply with this delta minus K, and then take the limit delta goes to K. So this just picks up the residue of this O delta at K. This gives the definition of soft current. And the feature of this soft current is that they just correspond to some symmetry. And for hard operator, they are just this O delta J, but the conformal dimension does not coincide with any value here. So in the study of scattering amplitude with soft particles, then the scattering amplitude will become ambiguous if the soft particles if we have multiple soft particles with mixed helicity. So the resulting amplitudes depends on the way of taking soft limits. So to sidestep this this problem, I will only consider positive helicity soft particle with positive J. So let me so previously I talked about this soft theorems and what identity. So now I can give you more details. So in the soft limit, so one of the particle has vanishing energy. So this PS goes to 0. Then this n plus 1 point amplitude will become n point amplitude just by some factor called soft factors. So it has Laurent expansion. So then we have this leading soft factor, sub-leading soft factor, and so on. And this leading soft factor is proportional to omega to the minus n with specific n. So if we perform manual transformation, then I claim this gives what identity. This can be seen as follows. So we have this omega to the minus n, as I show you here. Then we perform manual transformation. Then you will see that there's a power here. This means this soft factor omega to the minus n will become a power of conformal dimension Rn. And this enables us to introduce this current Hn equals to O delta multiply delta minus n, and then take the limit delta equals to n. This is definition is just what I introduced before. I can give you one explicit example. For example, for gluon scattering, the leading soft theorem for positive helicity gluon has the following soft factor. So we have in particular, we have this pj in the numerator. So this means we have this omega s to the -1. So if we consider the soft theorems with this soft factor here and perform manual transformation, then we will find the following word identities. So in particular, you will find that you have this operator corresponding to soft gluons, and it multiply with delta -1, and in the limit of delta goes to 1. So this becomes this Asymmetic current in this context. So on the left-hand side, we have this hard operators with this current insertion. On the right-hand side, we have the correlation function of hard operators, but with these extra factors. And this is just standard word identity associated to this Asymmetic current. So you can do similar things for graviton, etc., and you will always find different types of word identity. So now I will discuss this OPE.
Sorry,
so,
what was lambda on the previous slide?
Lambda? Which lambda?
Large lambda.
Yeah, lambda is essentially infinity, but for this to show this, you can just see that you have some regularization. So lambda is finite, and finally you take lambda to infinity, because if this is 0, then this doesn't matter, is 1.
Mm-hmm. And z equals zj. So like in terms of amplitude, that means like a collinear limit, right?
Which one?
Like, I mean the pole, z like equals zj. Like the red.
Oh, this one?
Yes.
Yeah, this is just a Holographic limit. I will now discuss it.
So essentially you somehow like mix soft factor with collinear factor, right? Like you take
I'm
a soft
sorry,
limit.
can you say it again?
You take the soft limit, and eventually you find some sort of a collinear singularity. Or
yeah, but here this G and Z and ZJ, I mean they are not necessarily close to each other. They are arbitrary. So I don't require that they are very close to each other. Yeah, but indeed they are related, and I will show actually from this collinear limit I can derive this soft theorems of word identity. But at this step, I mean this and they are arbitrary, so they don't need to be very small. So it's not a it does not correspond to any collinear limit at the moment.
Mm-hmm. Okay, thank you.
So now I consider this collinear limit. So this means that we have two momentum which are becoming parallel to each other. And in this case, we can consider the sum of two momentum. So which means that these two particles essentially are fused to one particle. And this P1, P2 are null. So in this limit, this total momentum P is also null. In this limit, the scattering amplitudes factorized as follows. So we have m point amplitude with 1, 2 collinear. Then this 1, 2 can essentially become one particle. So we have this m minus 1 point amplitude. But we also have some prefactor called the split function here. So in this collinear limit, P1 dot P2 goes to 0. And you can also use previous parameterization of P in terms of omega and x. You will find that this P1 dot P2 is x1 minus x2 squared. So in this collinear limit, this x1 just goes to x2. So in terms of this picture, so we have this collinear momentum, and on the stratosphere, this means these two particles are very close to each other. And this is just the limit for operator product expansion. So more precisely, we can perform the manual transformation on this split function, and then we will obtain the celestial OP. So we can look at the one explicit example. So we have this gluons scattering with the following split function. So we have two positive heliocentric gluon. It will become another positive heliocentric gluon. So this is the formula for the split function. We can perform manual transformation. Then we have this OPE. So here we have this O delta plus A. So delta is conformal dimension, plus is a spin plus 1, but it's just the helicity of this positive helicity gluons, and A is the color index. So we just put two such operators together, then we get another gluons with positive helicity and the color index C. Also, the dimension is shifted. So in particular, we have this power Z12. And furthermore, we have this beta function. So this is unusual for standard CFT, but it's important for special CFT. In particular, if data is some negative integers, then we will have a power. And that is consistent with my previous definition of a soft current, just to soak up this power. So we can do similar things for this graviton and obtain the celestial graviton OP. So this plus 2 means it's a positive helicity graviton. We put two together, then on the right hand side, we have this kind of positive helicity graviton operator. So far, this celestial operator product expansion is obtained from the collinear factorization of scattering amplitude, but it can also be obtained from the string worksheet. So, but I'm not going to talk about it here. So I'm not going to discuss this infinite dimensional symmetry algebra, but there are several ingredients. So now I'm going to introduce the ingredient. The first ingredient is the mode expansion of soft current. So I will work in 4 dimensions, but with 2,2 signature. This means that here Z and Z bar are independent. And in this case, we have Lorentz group SL2,2. Locally, it's just SL2R times SL2R bar. So if you are familiar with BMS story, you know that this kind of Lorentz symmetry can be enhanced to this super rotation, and it's given by Sora times Sora bar. But today I'm not going to talk about the full enhancement. I will only consider this chiral enhancement. So only the left chiral part will will enhance to this Varasora. So the actual symmetry is Varasora times SL2R bar. And in this case, we can decompose the soft currents, which I introduced before, into various chiral currents. So we have this soft currents, and then it can be has this Rowan expansion in Z bar, and the coefficients are just the chiral currents. So in total, we have J plus 1 minus K chiral currents, and they transform in this representation of SL2R bar. So here we have this coefficient, and but it's more convenient to rescale this chiral currents by multiplying with this factor I minus 1 minus n factorial times I minus 1 plus n factorial, and this gives rise to calligraphic R. So this extra factor is to simplify the formula for later purpose, but it also has physical meaning. So physically, this can be understood as light transformation. So in 2D CFT, for 2D CFT in Minkowski signature, there are 2 null directions. So we can perform a light transformation along 1 null direction. So we take this primary operator, we multiply with this factor, and then we integrate along 1 null direction. So this gives rise to another operator, which is a light transformed operator with weight h and 1 minus h bar. So we can consider the light transformation of this soft current or soft operator. So we can plug in the mode expansion, then we will find this formula, which is very simple. So we see that here we have this calligraphic R, which is exactly what I defined here with an extra factor. And up to this overall factor and this sign here. So essentially we see that this calligraphic chiral current are just expansion of this light transformed soft operator. And this is a physical interpretation of this rewriting. So now I'm going to talk about the second ingredient, namely the summation of SL2R bar descendants. So generally we have this OP with this structure. We have 2 primary operators. We put them together, we get another primary operator with some kinematic factors as well as some coefficient. But also we have these dots, which are the descendants. So in this talk, I want to sum over all the SL2R bar descendants. And this can be done by using the so-called OPE block. So on the right-hand side, we have this OP, and we multiply it with this 3-point function among this O1, O2, as well as the shadow of this O3. And then we just perform this integral from Z2 bar to Z1 bar. So since this 3-point function is uniquely fixed in CFT, so we have this very explicit formula for this OP block. And we can apply this OP block in this formula and obtain this formula. And this gives the OP with all SL2R bar descendants. So essentially, once you have the OP with primary contribution, this formula enables you to include all the descendants. So here especially, we see that C becomes N, and we have this kind of integral. So with all these integral ingredients, we can now derive this holographic Chiral algebra, which arises from this subset of OPE. So we start with operator OPE between graviton and matter. So here, this is a graviton operator, and this is a matter operator. And they have the following OP that becomes another matter operator. This generalizes the previous graviton OPE. And this just comes from the minimal coupling between gravity and matter, and they have the same universal coefficient due to the equivalence principle. So we can now apply previous summation formula to include all the SL2R bar descendants. So essentially, the right-hand side is replaced by this following integral. And now we take a soft limit. So we just set the dimension delta 1 to k, and k can be J1 or J1 minus 1, etc. And similarly for J2. So in this limit, these two operators will become soft currents. And similarly, also the right-hand side can be simplified. So then we will obtain the OPE between two soft currents. So as I said before, these soft currents can be decomposed into chiral currents. So we can pick up specific chiral components by considering the coefficient of this Z bar to some power. And then we will find the OPE between two chiral currents. So if you do this computation, you will find this formula. So here we have this graviton chiral current, and this is matter chiral current, and this gives us another another matter chiral current. So this is the coefficient, and with some simple power. So previously, this J1 is arbitrary, but we can consider different values for J1. So in particular, I will consider a supersymmetric Einstein-Yang-Mills theory. So in this case, we have graviton, gravitino, gluon, and gluino. So we can take J1 to be 2. Then we have this another graviton. So the previous OP becomes this one. So between two graviton. So if we set J1 to 3/2, then we get gravitino, and then we have the OP between gravitino and graviton, which is another gravitino, and similarly for gluon and gluino. We also have this Yang-Mills interactions. If we repeat the previous computation, you will find this chiral OP between two gluons, and this is a chiral OP between gluon and the gluinos, which is another gluino. And we also have this OP between this gravitino and gluon, which is another gluino. And finally, the chiral OP between two formulaic currents are 0. So it means there's no singular part. So we have this bunch of OPs, and this defines an algebra. So this algebra is generated by this infinite chiral currents here. So I will call it a holographic chiral algebra. So we can take a closer look at the graviton case. So we have this two graviton chiral OP that gives another graviton chiral current. We can convert this OP into commutators, and we find this commutation relation. So as observed first by Strominger, this is just W1 plus infinity algebra, or more precisely, the loop algebra of the wedge algebra of W1 plus infinity algebra. This is called a loop algebra because this is actually a Casimuli algebra. And the wedge algebra comes from the fact that here the n and m, they are restricted in the wedge. So it goes from 1 minus I to I minus 1. For simplicity, I will just call W1 plus infinity algebra. In particular, this H10 is a central term because the commutator with all the rest of currents is 0. And what's more, if we just take this H3 halves, H2 and H5 halves, and consider the commutator, then you will find that you can generate all the HIN. So this means that the infinite tower of chiral currents are generated by these 3 chiral currents. And they just correspond to the leading, subleading, and sub-subleading soft graviton. So this holographic chiral algebra is also generated by this 3 set of currents. How much time do I have?
Like 3 minutes. You can take a bit more if you need.
Okay, thank you, yeah. So now we have this infinite dimensional symmetries. So what's the implications? And in particular, what are the corresponding what identities? So previously we derived this algebra from soft OP. Now I can derive the what identity from soft hard OP. So we start with OP between gravity and matter as before, and we sum over all the descendants also as before. But now we will only consider a soft graviton. So we will take the dimension delta 1 and to 2 or 1 or 0 up to minus infinity. But this delta 2 will be generic, so it's a hard operator. So in this case, this graviton will become a soft current. And then we will find the OP between soft current and hard operator. Also, on the right-hand side, this integral will become this finite series. So it's a finite sum. So this OP just gives the action of symmetry current HL here on the hard operators. So my claim is that I can use this OP in correlators and find infinite graviton what identities. So on the left-hand side, I want to evaluate the correlation function of this hard operator with soft insertions. So I just replace this soft graviton current with any hard operator with their corresponding OP here. Then I sum over all the hard operators. Then I will just find the right-hand side. I claim this is just the graviton what identity. So this procedure is somehow not exotic. For example, in the stress tensor what identity, we have this stress tensor here and some primary operators. So we just replace the stress tensor and the primary operators with the OP, and then sum of all the primary operators. And that is essentially the stress tensor what identity. So my procedure here is exactly the same. So since here L can take value from 1, 0 up to minus infinity, we have infinite graviton what identities. And equivalently, this means in the scattering amplitude size, we have infinite soft serums. So we can take different values for L. For example, at leading order L equals 1, we have for this simpler formula. So one can show that this is equivalent to the leading soft graviton serum with positive helicity after doing a Mellin transformation. And similarly for the subleading and the sub-subleading or soft serum. We can also perform shadow transformation. So in 2D CFT, if we have primary operator or HH bar, we can consider this type of integral transformation. Then we obtain this shadow operator with the weight H1 minus H and 1 minus H bar. We can apply this shadow transformation on the soft current and obtain the shadow current. And we can also do the computation on the right-hand side. And this gives rise to infinite shadow graviton what identities. In particular, at subleading order, the previous formula will become simplified as follows. So we have this square bracket term. If you are familiar with the Fourier CFT, then you will see that this is essentially the stress tensor what identity. Once we identify this part as stress tensor, So this gives a construction of a stress tensor in structural conformal field theory, and is defined as a shadow transformation of subleading soft graviton. So this was first observed by Strominger and his collaborator, but using a different method. Finally, let me mention some general results. So far we were mainly discussing this with graviton, but actually many results can be generalized. In particular, I will derive for general OP. So as I said before, this OP can be derived from the collinear factorization. So in the collinear limit, this n-point amplitude will become 3-point amplitude and n-1-point amplitude connected by a propagator. And the prefactor in front of this n-1 amplitude is essentially the split function. So it's given by the product of this 3-point amplitude and this propagator. So in 4-dimensional spacetime, so it's known that this 3-point function on-shear amplitude is uniquely fixed by locality and symmetry up to the overall coefficient. This means we have a very explicit expression for this split function here, because this 3-point amplitude can be written down explicitly. So using this split function, I can perform Marin transformation and obtain this very general celestial OPE arising from cubic interaction of spinning particles. So we have this O1, O2 with spin J1, J2, so they are arbitrary. And on the right hand side, we have another celestial operator with spin minus J3. So you see that this is very explicit, and they are just dictated by this symmetry and locality. So only undetermined thing just C, which is the EF decoupling for this cubic induction vortex. So with this general OPE, I can derive this general formula for what identities. So here we have this soft current RLJ, and if we insert this in the correlator with other operators, we will find this formula. It can be written in terms of the correlation function of hard operators without insertions, but with some extra complicated contributions. So this what identity is applicable to a massless series controlled by cubic inductions, and it also applies to fermionical series. And the previous graviton what identity is just a special case. So I can use it to discuss the EFT question to graviton what identities. So this graviton is soft series. So we have this soft leading soft serum, subleading soft serum, and sub-subleading soft serum. So this is S0 is known to be exact, and S1 the subleading soft factor is known to is known that there is no EFT correction, but has one loop quantum correction. But the sub-subleading order, we have this EFT correction. In this case, we have this red part, and this is the sub-subleading EFT correction. So we have this previous general formula for what identity. So in this case, it turns out the interaction responsible for this correction is gives rise to this OP, and we can then convert this OP into what identity using the procedure I showed you before. And in particular, in the very special case, A equals -1, we have for this formula. So we insert the sub-subleading soft graviton in this correlator. So on the right hand side, we have for this correlators without current insertion. So it's easy to show that this what identity is equivalent to this sub-subleading the EFT correction to the sub-subleading soft graviton theorem once you perform Marin transformation. So this gives a simple check for the previous general formula. It also in a very simple example. Now I will conclude now. So in this talk, I discuss two types of symmetries. So global symmetry. which includes the Poincare conformal and the superconformal symmetry in X4 with Yang-Mills. I present the explicit generators for this symmetry on the celestial sphere. I also discuss asymptotic symmetry from celestial conformal theory point of view. So I derive infinite dimensional symmetry algebra called holographic Chiral algebra from this soft OP, as well as this corresponding odd identity associated to this infinite dimensional symmetry. And also, I just present a general formula for celestial OPE from cubic inductions. The content can be nicely summarized here. So starting from symmetry and locality, we can derive the celestial operator product expansion. And then by focusing on the soft sector, I derived the infinite dimensional symmetry algebra, holographic Chiral algebra. And furthermore, the corresponding infinite word identities. So these infinite word identities are just equivalent to the infinite soft theorems in scattering amplitudes. Of course, there are many open questions. So in particular, in this talk, I was focused on the positive helicity particles because of the ambiguities induced by this negative helicity particle. But nevertheless, we should include them finally. But the problem is how do we include the negative helicity soft particles? And furthermore, most of the discussion here are at the tree level. So how about the quantum corrections? And also, how about the multiple soft theorems? Do we have similar picture? And finally, maybe the most important question for celestial holography is, can we find an exact model for celestial holography? For example, can we realize celestial holography in string theory? So with this question, I will stop here. Thank you.
Thank you. Are there any questions? Can you comment a bit on this like infinite dimensional symmetry algebra that you discovered in celestial terms? So it should be also seen in usual amplitude terms, right?
Yeah, that's the point. Because, for example, we have this infinite theorem, so it's not simple to find in traditional framework. Indeed, people previously found some infinite soft theorems or conformally soft theorems, but they are quite complicated and the derivation is not clean. So here, and also in the traditional framework to derive this asymptotic symmetry, so normally people will just perform the asymptotic symmetry analysis in the bulk and then find the symmetry algebra. But here, I was starting from the celestial conformal field theory. Starting on the boundary, I derived this infinite dimensional symmetry algebra. So it's not obvious to see in any case. So somehow this is, I think this may be the first new results in celestial holography in the sense that, I mean, these results which cannot be derived in a traditional way. And previously, most results in celestial holography are somehow rewriting. So for example, this kind of leading subleading soft theorems, essentially it's just perform many transformation and get something in celestial CFD, but there's no essential new things. But I think this infinite dimensional algebra, like this W1 plus infinite algebra, is new. So people would never expect from this traditional scattering amplitude in the past.
Mm-hmm. Thank you. And can you explain what was like this EFT correction to soft factors and what was the difference with loop correction?
What correction?
EFT.
Yeah.
And loop correction.
Loop correction. Okay.
So EFT, you mentioned EFT corrections, yes, and loop corrections. So
yeah. So here we have this soft graviton theorem. So we can perform this Rho expansion in the soft energy. So we have these different soft factors S0, S1, S2. So this is a leading soft factor, and it can be shown that this is exact. and at the sublinear order. So it has one loop quantum corrections, but there's no EFT corrections.
And what does that mean? Like no EFT correction? Like what kind of effective theory you have in mind?
So it means that you can, because here I'm just here it means this is Einstein gravity. So by EFT means I can just ask a higher derivative of operators in this Lagrangian and compute the scattering amplitude, and then check this soft factor. So you will see that at this order, there will be no correction from these high derivative operators. But if you even in Einstein gravity, you can compute the loop correction, but you will find indeed you will have some quantum corrections at one loop for this soft factor. But at the sub-sublin order, you will find that there are even EFT corrections. So you can write down some EFT operators and compute the amplitudes with these EFT operators, and find that at this order you will find this EFT correction. So here I think I have the explicit formula. Let me see. Yeah. So we can write down this set of higher derivative operators. For example, this is phi RR. So if there's a non-scalar, then we have this EFT operators, or this IF square, or this R times some formulas. So if we include this term in Lagrangian and compute the soft theorems, then you will find that at this sub-sublin order, this soft theorem is not true anymore, and you need to modify in this way. So you need to add this term in red.
Okay, I see. Thank you.
So essentially, this EFT corrections captures quantum correction from this massive fields, because you can integrate out this massive fields, and then you are left with some EFT operators. But if you consider massless fields, then you cannot integrate out. That's why, I mean, still you need to worry about this one loop corrections.
Thank you. Any other questions? Okay, then we'll thank the speaker. Thank you for a nice talk, and yeah, to everyone, we'll see you next time.
Thank you for the invitation.